Awesome. Hi, yeah. So I'm Lauren Henderson. I'm a grad student at Notre Dame. I'm going to tell you guys about some of the work that I've been doing on Deimos, where I study how dwarf galaxies around the Milky Way evolve and how heavy elements on the periodic table are made. So my work broadly falls under the umbrella of galactic archaeology, and one of the main premises of galactic archaeology is that the element abundances in old stars can tell us things about the past. We can learn about the star formation, histories, and general evolution of galaxies, about the properties of the very first stars, and also about how we build the periodic table of the elements in space. So to illustrate this, I have a couple cartoon plots, but do not worry, we'll be getting to real data soon, I promise. But these will hopefully help us frame our mind. So the first is showing how metallicity changes over time since the Big Bang. And what I want to point out is that metallicity is increasing monotonically over time. And this is not metallicity in a single star, but metallicity in a population of stars. So as stars live and die, they enrich the ISM with more metals. Subsequent stars can form with higher metallicities. This means we can take metallicity as a proxy for time. We can then use this to compare metallicity, for which we usually use iron, to abundances of other elements in stellar populations. So now we have metallicity on the x-axis, but we can still think of that as time. And on the y-axis, we have two different elements, magnesium and iron. A plot like this can help us compare the timescales on which these elements are produced. This is a good example because magnesium is released in the deaths of really massive stars. That happens really quickly, whereas iron is released in the deaths of lower mass stars, like in type 1a supernovae, and that takes more time. So we can see that at early times, we have a higher magnesium to iron ratio because there hasn't been time for a lot of iron to be released in those low mass stars. So we just have the high mass stars dying. Then as time goes on, that ratio is pushed down as we start producing more and more iron. So like I said, I'll be showing some real examples of these plots. And in particular, I look at neutron capture elements in dwarf spheroidal galaxies around the Milky Way. Dwarf spheroidal galaxies are really cool to study because they are great laboratories for galactic chemical evolution because they're old and they're simple. So this is a picture of the Sculptor dwarf galaxy. It looks pretty different than some of the other pictures of galaxies we've seen today because it doesn't really have a lot of dust and gas, and it doesn't have any star formation. Kind of just looks like an overdensity of stars. But that's exactly what makes it a good place to study how new elements are made and how old stellar populations evolve. Now, like I said, I look at neutron capture elements, and I thought I should give a little introduction to what this is. This is the most nuclear physics we're going to be doing today. But elements heavier than iron need to be made in a different process than nuclear fusion in the cores of stars. And almost all of them are made in neutron capture, which proceeds as this picture shows. So you have a nucleus capture a free neutron, and then eventually that neutron can beta decay into a proton, and you move up to the next element on the periodic table. Now, there's two main types of neutron capture nucleosynthesis. There's the slow or S process and the rapid or R process. And whether you're in the slow or rapid process depends on how quickly you're capturing those neutrons. In the rapid process, you're just shoving tons of neutrons onto nuclei, and then eventually they'll decay. So the S process primarily occurs in evolved intermediate to low mass stars that are on the asymptotic giant branch, where they're no longer fusing anything in their core, and they're instead fusing hydrogen and helium and shells around the core. This just happens to be the perfect place to produce free neutrons, the S process. The R process, on the other hand, is a really open question and a really hot topic in galactic archaeology and nuclear astrophysics as a whole. Now, there's really good evidence that it occurs in neutron star mergers, which makes sense, lots of neutrons there. But we're not sure if those are the only or even the primary place that the R process happens, especially at early times. So to kind of put all of this background together, I'll reiterate that dwarf spheroidal galaxies are really great for studying galactic chemical evolution because they're old and they're simple. Our process elements, we want to measure them because we want to understand and constrain where they're formed. Like I showed you with those cartoon plots, we can start to understand the timescales that elements are produced on by making plots like that. And if we understand the timescale that our process happens on, we can start to constrain where it's actually happening. S process elements, on the other hand, are really cool to study because we know exactly where they're formed. So we can use them as precise clocks to trace back when star formation was happening in these dwarf galaxies. And for all of these science cases, we benefit from a large set of measurements, which is where Deimos comes in. So Deimos is the multi-object spectrograph on Keck, and we can use it to get spectra over a wide wavelength range of lots of stars at the same time. This is really great because typically neutron capture abundances are measured with high resolution spectra, which greatly limits the number of abundance measurements we can get in these galaxies. But if we can use medium resolution spectra, and get lots and lots of measurements, we can even better characterize how these elements are changing over time. The caveat, of course, is that we're using medium resolution spectra now, which is a bit more difficult. So to combat this, we use a spectral modeling code to model all of the lines of the element of interest simultaneously. This way we can take advantage of pretty much all the information the spectrum has about the element of interest. So this plot is an example of that. It's europium measurement in a star in Sculptor. So each panel is a 20 angstrom region around a europium line. The line itself is in green. And then the red is the best fit spectrum, while the blue is a spectrum, model spectrum that has the same stellar parameters, but no europium. So you can see that none of the lines on their own are very good, but they do contain information about the amount of europium in the star. And by combining all of them, we can get pretty good measurements. So here, as promised, are some real data. This plot is showing metallicity on the x-axis. So again, we can take that to be time. And now on the y-axis, we have the ratio of europium to iron. And a reminder that europium is one of our process elements. So we're interested in learning where it's made. We can kind of split this plot into two main regimes qualitatively. In earlier times, we have a large scatter in europium and a higher europium abundance. And then at later times, europium to iron starts to decrease. Now, if you're very astute, you might recognize it looks very similar to the cartoon plot I showed you earlier. And of course, I'm not going to make any bold scientific claims comparing my data to a cartoon plot, but I will suggest that this does imply some amount of europium is probably made on timescales faster than iron is made. And this has implications for where the R process can happen. In comparison, we can look at the same plot but for an element made in the S process, barium, and you can see it has a very different shape. As time goes on, it's kind of just remains a blob. Maybe it's increasing slightly. And this is because barium takes longer to produce. You have to wait the entire time for a low to intermediate mass star to evolve onto asymptotic giant branch. And then one more way we can compare the nucleosynthesis in these dwarf galaxies is to more directly compare two elements. So we can plot the ratio of a primarily S process element like barium to a primarily R process element like europium, which is what we have on the y-axis. And the x-axis is still metallicity, so we can still think of that as time. Now, the horizontal lines are the barium to europium ratios we would expect if only the R process was happening or only the S process was happening. So we can see that at early times, all the abundances are hovering around that pure R process line, which makes a lot of sense because there hasn't been enough time for asymptotic giant branch stars to start producing a significant amount of barium. Whereas at later times, we start to see that ratio pushing up towards the pure S process line when we start getting lots and lots of barium production in these stars. One thing I also think is kind of fun to point out that we get to see when we have so many measurements is there's more structure in this data than when we more sparsely populate it. And so there's this weird decrease from metallicities of -2 to -1.5. And of course, without comparing these measurements more quantitatively to models, it's kind of hard to predict what's actually going on here. So it doesn't really align with what we would expect to see. But one possibility is this could be a contribution from a process that makes the S process faster, something like fast rotating massive stars that are expected to also have S process production. But yeah, that's just one of the kind of exciting bonuses we get when we start getting lots and lots of neutron capture abundances in these dwarf galaxies. And then kind of off topic, but just to finish off my talk, wanted to give a shout out to the DMOS throughput upgrade, which will hopefully be going to Keck early 2025. And it'll be especially improving throughput in the blue wavelength range, which is where the neutron capture lines are. So DMOS is already great for doing galactic archaeology, but hopefully it's only going to get better. And this summer, I got to go to Keck for all of July and work on the pressure compensation system on DMOS. So if you have ever used DMOS, you've seen that blue box, and it needed to be updated to be ready for the upgrade and also just kind of generally improved. So that's what I was working on. And so yeah, in conclusion, DMOS is really great for doing galactic archaeology. Using medium resolution spectra, we can get lots and lots of neutron capture abundances, which opens up a lot of possibilities for cool science. I only showed you pictures for Sculptor, but I also have looked at 4 other dwarf spheroidal galaxies around the Milky Way. And then, of course, I am updating at FCS. So if you have FCS questions, I'm also open to those. Thank you.